So I get to introduce myself, which is cool. Hi, I'm me. I'm Jim Thatcher. I am an assistant professor at Oregon State University. I do a lot of research on intersections of data, capitalism, and like renewable energy, among other things. But today, I'm going to be talking about this really cool project that I've been doing with Craig Dalton of Hofstra University that's there, and Meghan Kelly of Syracuse University, who is in Syracuse. And we've been working, thinking, and talking through it for a bit of time. And while we've drafted this piece, it's still a work in progress. So we're trying to think through what audiences it matters for and whom it might most benefit from actually making this argument to strike this balance between what might be obvious to a cartographic audience, but not to a larger geographic one, and vice versa. So thoughts, feedbacks, and criticisms are really welcome here. And away we go. Unfortunately, we can't cover the full range of our argument here. However, I wanted to first explain the underlying ideas and impetuses behind the work briefly, before then offering two specifically cartographic examples. First, the relatively commonly understood idea of projections shaping resulting data interpretations, something that, at least today, at least in this audience, is covered passingly in most intro cart and GIS courses. And then a more subtle one that actually sort of sparked this project around the algorithms that generalize maps. I'll end with a bit of a summary that gestures out situating this work within broader narratives of algorithmic harm and bias, but tying them directly to our, and here I speak for cartographers and mappers broadly, role and consideration in these processes. Again, though, I'd like to emphasize that this is an incomplete picture. Like, we also have a whole section on symbolization that I just had to cut for time, so bear with me. The very first thing I want to do is highlight, why is there nothing there? Oh, cool. Very first thing I want to do is highlight what we mean when we talk about technological and algorithmic harms. There's two very important reasons for this. The first is to emphasize that this is not a technological determinist argument. The second is that our goal here is following in the footsteps of other critical geographers, STS scholars, critical cartographers, and so forth, in trying to move past a pure harm-based thinking through of algorithms. But to do that, we do need to briefly note what we mean when we talk about harm, so that we can then situate how to move past it. Two quotes help us to situate what we mean here. The first is from Mimi Anuha's definition of algorithmic violence, where algorithmic violence refers to the violence that an algorithm or automated decision-making systems inflicts by preventing people from meeting their basic needs. And the second is from Sophia Malson. She sort of extends and summarizes this view a bit when she says that algorithms treat people unequally because of the bias that is coded into them via the individual and institutional ideologies behind them, and so forth and so on. There are a few underlying assumptions that rest here that are worth reiterating. The first, again, is not that this is a unidirectional process of control. There are generative, hopeful, joyous, and subversive uses of algorithms in our daily lives. The second, though, is that in our society, our lives are largely modulated with and through algorithms. Understanding the underlying choices that they normalize, even in cartography, is crucial in finding those joyful and subversive moments. And we'll return for that in a bit. But for now, let's focus in on maps. And by and large, we use computational devices to both create and look at maps. Sure, we all have print maps. Hell, I love them, hang them up all around my house. But day in and day out, our maps are largely produced on and displayed through digital screens. The formal code-based algorithm has largely replaced the pencil and ruler, which, you know, for me is great because I can't draw worth a dang, but your mileage might vary. And I learned to make maps on something like this, which makes me somewhat old. But as we all know, time marches on and technology changes. Today, someone using software from that self-same company would open a new project and be presented with this. It's not so different that anyone familiar with one would be wholly unable to use the other. And both follow larger patterns of software development and norms in the West, like where buttons are placed, what they do, how they work. But there's a difference that struck me, and it's one of the impetuses that sparked this project, and it's right there. It might seem small or insignificant, and certainly it is useful for many of us on a day-to-day basis. But the world to be mapped has effectively gone from a blank slate in which you bring what interests you in and is of importance to be displayed, to one which the world exists and you layer additional data on top of it. That's the default. That's what you get when you just open the software. Of course, I can unclick those data layers. I can even change the defaults to not include them if I really, really want to. And of course, not everyone is making maps using Esri software. Alternatives exist and abound. Again, this is not a determinist argument. It's about norms and defaults. We're attempting to highlight how these norms undergird what we do, how they become defaults, and in so doing, how they're baked-in assumptions, they're representations of the world, from color to size to orientation, become taken for granted as we build our own maps on top of them. So as we know, I think in this room I can say that, I can't say that in every room, map projections involve converting the Earth's three-dimensional surface into a two-dimensional map. And that, just mathematically, when you reduce dimensions, you're going to lose some aspects of your information. So it presents cartographers the important choice of what projection to use, and this choice is complex. It involves not just formal geometric qualities, but also social context and recent technological changes. Given that complexity, there is an understandable temptation to let the system default to choose the map projection. And many map makers do, even as this has consequences down the line. For example, while Arc Pro from the last slide defaults to a web Mercator, which we'll return to in a moment, in the old Arc Map software and in current QGIS releases, the image of a map in a new blank project defaults to an equirectangular projection. This unnamed projection is efficient and it avoids having to render in 3 dimensions. One of us, and we won't say who, observed a tenured GIS professor colleague describe how a map in ArcMap was unprojected, even as the map itself is on the screen and was two-dimensional. In this case, the GIS data itself was unprojected. It's stored coordinates defined on a datum, a three-dimensional surface. And this colleague even added a layer of circles to the map in an apparent attempt to show how the unprojected map did not distort them. These circles did not demonstrate the distortions of an equirectangular projection. These are not TSAT indices. They're just not. Our colleague's confusion is understandable. The map's properties listed the coordinate system as categorically unprojected, a geographic coordinate system rather than a projected coordinate system. The problem is that the map visible to the class was projected. The software rendered that data on a map on the screen in the GIS software in 2 dimensions on an unnamed projection chosen by default. While wholly understandable, that confusion shows a somewhat low stakes but still significant example of how defaults end up by consequences. That day, the stakes were some confused undergrads, and that's okay. Sorry. These are actually what they look like. Perhaps no projection's popularity has benefited more from technical shortcuts and default algorithms than Mercator. At least part of its popularity stems from its navigational utility, but over the centuries, the projection frequently served not only for navigation, but in scientific educational contexts, as well as throughout popular culture, including feature films like Willy Wonka, oops, that's not Willy Wonka, War Games, CBS television news, and even satirical television news backdrops like The Daily Show. There we go. Due to its distortions and misuse, the Mercator projection has had many critics ranging from Max Eckert to the Surrealists, but nothing compares to the controversy sparked by Arno Peters. As many of you know, Peters was a filmmaker and historian who explicitly condemned the Mercator projection and those who chose to or acquiesced into using it for perpetuating a racist colonialist worldview that minimized the relative size of current and former colonies while exaggerating the size of mid-latitude colonial metropoles. We don't want to delve deeply into Peters' controversy. Crampton covers it really nicely, has a great article on it if you want to read it. But it's important for the popular appeal of Peters' criticism of the Mercator projection. That helped open the opportunity for more considered choices in how the world appears projected in maps. Moreover, unlike Eckert, Peters accomplished this in popular cultural discourses, from UNESCO to a West Wing episode. And in retrospect, cartographers could have more effectively pushed for Mercator in that moment, but we didn't. And yet, a few years later, Mercator comes roaring back. Why? Because the Google Maps adopted Web Mercator projection. And Google Maps in the 2000s was immensely influential, not just in its technical systems, but its cartographic design as well. And Craig has written extensively on this, as has Tim Wallace. Thus, Web Mercator became the standard default projection for most other mapping applications, web mapping applications, at least initially. From OpenStreetMap, Bing Maps, Here Maps, Esri ArcGIS Pro, Mapbox, and Apple Maps up to certain scales have used it or still do. And in this context, the Mercator projection has two strong technical characteristics that matter. First, on a very local scale, the scale of most consumer users, Web Mercator is very nearly conformal. Battersby et al. 2014 explore this in detail. And the distortions do not make much practical difference at low and mid latitudes where many of the users were located. History builds on itself. Second, it is rectangular. North is all the way across the top, and it seamlessly fits frames on websites. However, all of the previous critiques remain. It's not like they changed. The popular imagination of the world as Mercator, through its default status on web maps, normalizes its distortions and sets visual expectations for users' perceptions and understandings of the world. You can choose a projection in ArcGIS Pro or Mapbox, but oftentimes people don't. They just stick with what's there. You're in a hurry. You don't, or you don't even realize what's happening. And this isn't an argument from privilege, right? It's not like some of us, we know better, but that's because we got to. Anecdotally, and despite all of our best attempts, if our introductory mapping and GIS students are asked to name a projection, the vast majority will reply with Mercator. It's the one people know. The persistence of Web Mercator is a crutch in popular map discourse. It's easy because it's ubiquitous, a built-in preset facilitated by centralized web technologies leveraged by centralized technology firms. But that preset figures how we see the world. More thematically appropriate and socially conscious choices require both knowledge of and choice to find those alternatives. The default normalizes a specific view. And so now I want to switch gears a little. Generalization offers another arena to examine what we're calling algorithmic taken-for-grantedness in cartography. Simply put, generalization involves a series of techniques and decisions for meaningfully adding or removing features and feature details from a map. In the classroom, generalization is coupled with discussions of scale and the impossibility of mapping everything that exists within a spatial extent. Usually, because we're all kind of nerdy, we point to that old story about the impossibility of a one-to-one map. Generalization can be applied to content by selecting or not selecting particular map features. It can also be applied to the geometries of map features by simplifying, smoothing, aggregating, collapsing, yada, yada, yada. You get the drill. Being at NACIS, it would be remiss not to highlight the incredible resource of Natural Earth. For those that may be unfamiliar, Natural Earth is a NACIS initiative taken up by Nathaniel Kelso and Tom Patterson in 2008, among many more volunteers, that offers a slew of global geospatial data at 3 map scales. It's currently in its 6th iteration, and it's an incredibly useful resource for professional practice, teaching, and research. This data set is one data set among many that is impacted by what we're talking about, though, in ways that can cause unintentional harm. So speaking of equirectangular projections, Natural Earth offers global admin 0 or country-level boundaries at the 1 to 10 million, 1 to 50 million, and the 1 to 110 million scales, and provides guidelines on when or how you might utilize these data sets given your scale, and extent, and context. Again, this is a super useful data set. These data are ready to go out of the box. You don't have to conduct your own geometric generalization operators like simplification, which for many of us is really useful when we're in a rush or we're just trying to get beginning students to start working with this data. In many cases, these data may not have immediate ramifications for everyday life and how we understand the world. However, what happens when generalization operators literally remove or erase places from the map? In our present context, this can have immediate impacts, reinforcing particular narratives and geopolitical agendas that we may be all too familiar with. This was one example of generalization erasure that Meghan stumbled upon last year, whereby when she was working with this data, if you go to the 1 to 110 million scale, Gaza is removed from the map. This is by no means a new concern, as we see similar erasures with small island nations that might not be visible at a global scale. And to counteract these erasures, we have developed generalization operators and even map projections that prioritize and highlight to visually amplify these small island nations at times. Yet examples like this one in Gaza aptly illustrate algorithmic harm, inadvertent or not, intentional or not, and the taken-for-grantedness of generalization. Right? This is an amazing data source, but it still does this. So how does this happen, and what do we need to watch out for? Oh, I said I would do this. Thank you, Jim. We need to pay attention to the algorithms and the decisions that we make in everyday mapping practice. MapShaper, another mapping tool produced by another NACIS staple, MapBlock, offers a visual GUI and a command line console for simplifying and editing spatial data and our subsequent map features. These methods are also similarly offered in QGIS and ArcGIS Pro. They're there in all of our tools. And as such, it's imperative to understand our generalization algorithms and how time-saving data sets and generalization tools like MapShaper have the potential to produce harm. The harms produced by algorithms occur. This is a little janky. Meghan made it, but and she was like, "I'm sorry," and I was like, "No, it's great. It does what I want it to do." The harms produced by algorithms occur simultaneously at both structural and societal levels, and in the mediation of individuals' quotidian practices, ranging from the looking up of directions to a nearby store to scrolling through algorithmically curated social media feeds. In this sort of brief talk, we've introduced our concept of the taken-for-granted nature of algorithms within aspects of cartographic workflows found within classrooms, government agencies, and research endeavors. These are processes that many of us use every day without consideration of the decisions that are being made as we do so, with the assumptions that structure, though not define, our outcomes. This, then, is the taken-for-granted world of mapping, or at least part of it, the part that we had time and knowledge to talk about. These algorithms undergird the production of maps, and as such, the means by which maps are used to make claims upon the world. Algorithms are not new to mapping. For example, machine learning approaches have long been used in remote sensing to classify land cover change from satellite-derived imagery. Much of what we know of the world is through these processes. However, in light of the simultaneous explosion of boosterism around algorithms and AI writ large, and the ongoing imbrication of maps with how individuals move through, come to know, and experience the world, it is imperative to identify and better understand how algorithms shape, influence, and process how maps come into the world. Okay. So the question that we're often left with after like a critical talk with that is like, all right, so what is to be done? Certainly we shouldn't and can't get rid of projections, and many maps would be of limited use without generalization as well. Rather, what we see are patterns whereby choices are made by algorithms or algorithmic defaults that then must be adjusted manually down the line by a person, and/or that have negative impacts for both people reading maps and people being mapped. So we're calling for two things. One is a greater attention to be paid to algorithmically selected choices in the design process, whether in classrooms or in professional workflows. And here Craig really wants me to quote Rush and say, if you have not made a choice, you still have made a choice. Is that right? I don't really listen to Rush, sorry. I do like prog rock, though. Recognition that even with greater attention to algorithmic choices, there are systems of power here, not just technical systems, delimiting what design choices can be made, necessitating critical evaluation by cartographers and readers, and if possible, strategic pushes to make choices and adjustments to said systems that consider not just technical pros and cons, but context as well. And many of the other speakers in this session are doing just that, and many of you all are doing that, just that now as well. So this is just sort of our thinking. Thanks. And I left myself enough time for exactly one question. Yeah, go ahead.
One of the things that I see...
Sorry, for our online recording folks.
Gotcha.
One of the things that I personally see a lot of people who are new to GIS and unexposed to cartography do is in Pro choose natural breaks. And I was wondering if you had thought about symbolization that way, and if so, if there's anything you can do to like approach these students. And I don't know, I find myself at a loss trying to tell them why that might not be the best choice.
So that is actually the third section of this article that I didn't talk about. And one of the things I do just is like a really, like when I'm just trying to breakthrough on my intro level course is Axis Maps has a really cool tutorial on breaks and where to use them online. And I just kind of send them that way. Because what I found is like sometimes, particularly in intro cart courses, some of the reasons why you don't want to use that are very mathematical, and it can be hard to be like in the middle of a I'm showing you color theory and we're doing this and I'm like, hold on, let me show you this equation. And so just giving them this handy tutorial that opens the door to consideration kind of gets the foot in the door and then allows for kind of greater expansion over time. And I don't think that's a solution, that's just what I got right now. All right, thank you all.